Hello, I'm Professor Scott Hadzik from Weber State University's Automotive Technology Department in Layton, Utah. Over the past 15 years, I've dedicated my career to teaching electrical diagnostics to automotive students. Through this experience, I saw a growing need for a tool that could bridge the gap between theory and the complex realities of computer-controlled electrical systems. That's why I designed and built the Magnetic Mat Electrical Training System, or MMTS, in collaboration with other faculty and the university. Before we dive into today's walkthrough, I want to share an exciting opportunity available at Weber State University. If you hold ASE certifications, we can help you convert that expertise into college credits. This program is designed to recognize your professional knowledge and help you take the next steps in your automotive career. Stay tuned until the end of the video for more details. In this presentation, our goal is to develop the skills needed to diagnose most faults in computer-controlled electrical systems. The MMTS is the tool I'm using to teach these concepts, but the focus isn't on the tool itself, it's on understanding the diagnostic process and applying it effectively to real-world systems. To help you follow along, let's take a quick look at how the MMTS works. This system is purpose-built to simulate automotive electrical circuits and provide a hands-on way to practice troubleshooting. It serves as a learning platform to apply the concepts we'll be discussing. The magnetic mat ensures that components like the battery, ECU, switches, and loads are placed consistently according to the printed circuit diagram. This allows us to replicate real-world scenarios while maintaining an easy-to-follow layout. The MMTS can be mounted on a whiteboard for classroom demonstration or laid flat on a lab table for individual practice. Its flexibility allows us to focus on building a solid understanding of computer-controlled electrical systems in any learning environment. The MMTS is built around a modular system of nodes, each representing a key component of an automotive electrical circuit. These nodes are designed to simulate real-world electrical components. In this section, we'll provide an overview of the nodes and their specific functions, helping you understand how they work together in a circuit. Each node is equipped with its own internal circuit protection to prevent damage in the event of incorrect connections. This ensures the longevity of the system and provides a safe learning environment for troubleshooting and diagnostics. Each node except the fuse can be set to an electrical fault. These faults include high resistance or open circuits, which provide realistic challenges for developing diagnostic skills. The MMTS is powered by a red power supply accessory. The unit houses 8 AA batteries and is designed to provide energy for the entire system. While it powers the MMTS, it isn't considered part of the circuit when troubleshooting. This accessory is especially useful in setups where mobility is key. It serves as a substitute for a benchtop power supply, enabling the MMTS to be used in classrooms, labs, and remote locations without access to external power. The battery node includes a built-in voltmeter that allows for a quick check of the battery's condition. While this meter provides a general reading, it's not as precise as a dedicated multimeter, but it's useful for an initial analysis. The fuse node contains a 2-amp fuse, providing an opportunity for students to learn about the importance of circuit protection. This fuse is rated well above the expected amperage of the circuit, ensuring it remains intact during normal operations while safeguarding against potential overcurrent conditions. Wire nodes are a key component of the MMTS. Each wire node features a gray housing consistent with other conductive nodes and is paired with a uniquely colored wire. This color coding allows students to quickly and easily identify which wire is being used in the circuit. There are 2 splice nodes, one green and one yellow. These nodes are used to create parallel branches within a circuit, replicating the way automotive wiring often splits to serve multiple components. Each splice node functions similarly to a wire node, but allows for additional connections to branch off. The circuit includes two splice right nodes and one splice left node. These nodes function similarly to wire nodes, but with one key difference. They allow for an additional branch to be added to the connection. The red latching switch node simulates the functionality of a flasher button commonly found in automotive systems. This node allows students to interact with a control device that mimics real-world operations. The three-way switch node simulates the functionality of a multifunction switch commonly used in automotive systems to control turn signal lights. Rocking the switch to the right activates the right turn signal, and moving it to the left activates the left turn signal. The LED nodes in the MMTS are color-coded light blue and dark blue, helping students visually identify these components as the load in the circuit. This reinforces the concept that loads are responsible for converting electrical energy into another form, such as light in this case. The ground block in the MMTS circuit serves as an anchor point for all the grounds, similar to a ground stud in a vehicle. These nodes help students understand how multiple grounds connect to a common point in automotive systems. The ECU node is the heart of the MMTS. Inside a computer chip continuously monitors inputs, processes data, and controls outputs. This mirrors the functionality of an actual electronic control unit in a vehicle, making it a central component for understanding computer-controlled electrical systems. The ECU has 3 inputs and 2 outputs, along with 1 power and 1 ground connection. These connections simulate the way a real ECU interacts with various components in an automotive system. Input 1 and Input 3 are monitoring their respective circuits for the presence of 12 volts, which we often refer to as a high signal. Input 2 is monitoring for a ground signal, referred to as low signal. These inputs allow the ECU to detect and respond to changes in the circuit just like a real ECU would. To simulate real-world problems, faults can be introduced on both the inputs and outputs, providing students with realistic troubleshooting scenarios. The ECU's 2 outputs control connected components in the circuit, such as turn signals. By interpreting the input signals and applying internal logic, the ECU determines when and how these outputs should activate. With its ability to monitor inputs, process data, and control outputs, the ECU node provides a hands-on way to understand how electronic control units function in real-world automotive systems. This insight is crucial for diagnosing and repairing modern vehicles. Now that we've introduced the system, let's start exploring how to develop an effective diagnostic process. We begin with a simple circuit and gradually build up to more complex computer-controlled systems, focusing on the techniques and logic needed for successful troubleshooting. Let's start with a simple circuit. Here we have a battery providing power, a fuse for protection, wires to connect components, a switch to control the circuit, and an LED as the load. The switch must be in the on position to allow current to flow through the circuit. With the circuit complete, the LED should illuminate, dropping nearly all the voltage as it is the only load in this setup. To demonstrate the diagnostic process, I'm going to introduce a fault into the circuit. As a reminder, any node in the MMTS, except for the fuse, can be independently set to a normal, open, or high resistance state. I won't show the specific steps for setting the fault to keep students focus on diagnosing the problem rather than identifying the fault's location visually. This will also illustrate how quickly faults can be introduced and diagnosed using the MMTS. I've introduced a high resistance fault on the green wire in this circuit. Since the LED is the only load, it should be dropping nearly all the voltage. We'll begin with a voltage drop test across the LED. If the LED isn't dropping most of the voltage, it indicates that the fault is located elsewhere in the circuit. To perform this test, place the red lead on the positive side of the LED and the black lead on the negative side. The voltage drop across the load in this circuit is expected to be nearly equal to the source voltage. However, the multimeter reading is close to 0 volts, indicating that the LED is not functioning as the primary load. This suggests a fault elsewhere in the circuit that needs to be addressed. To test the ground side of the circuit, place the red lead of the multimeter on the negative side of the LED and the black lead on the battery's negative terminal. This test determines whether there's proper continuity to ground and checks for an excessive resistance. A low voltage drop on the ground side confirms minimal resistance, which is exactly how the circuit should function. In this case, the ground side checks out, indicating it's not contributing to the issue. With the ground side verified, we'll shift our focus to the power side of the circuit for further diagnostics. Now, we'll troubleshoot the entire power side of the circuit. I'll place the multimeter's black lead on the positive side of the LED and the red lead on the battery's positive terminal. The reading is close to the source voltage, indicating that the fault lies somewhere on the power side of the circuit. With the power side identified as the issue, we'll now test each individual node along this part of the circuit. Starting with the fuse, we'll perform a voltage drop test. I'll place the red meter lead on the battery positive and the black lead on the wire coming out of the fuse. The fuse should act as a conductor with minimal resistance. A low voltage reading here confirms the fuse is functioning correctly. Since the fuse checks out, we'll move on to test the green wire next. To test the green wire, I'll place the red meter lead on the most positive side of the green wire and the black lead on the other side. The voltage drop measurement on the green wire is higher than expected, indicating that the wire has more resistance than it should. In a properly functioning circuit, the majority of voltage drop should occur across the load, such as the LED. This abnormal reading identifies an issue with the green wire that needs to be addressed. I will now replace the green wire, and we can see that this resolves the problem. With the fault resolved, the circuit is now functioning as expected. This example highlights the importance of using voltage drop testing to pinpoint high resistance and systematically troubleshoot the circuit. When you're first starting out with diagnostics, I recommend the following approach. Begin with a voltage drop test on the load to see if it's dropping the expected voltage. Then move to the ground side to check for any issues. If the ground side is functioning correctly, proceed to the voltage drop test on the entire power side of the circuit. This step-by-step process is a solid starting point and helps build your confidence and consistency in troubleshooting. Let's set up one more fault to ensure the concept of voltage drop testing is clear. This time I won't tell you which component has the fault. As you can see, the circuit is back to a non-functioning state. When I put the switch in the closed position, the LED does not illuminate. To start the process, I'll perform a voltage drop test on the LED. where the voltage should normally be dropping. The low voltage number here indicates that the fault is either on the power side or the ground side of the circuit. Let's check the ground side. A low voltage drop on the ground side indicates that it's acting as expected with very little resistance. Now let's check the power side of the circuit. The voltage drop here is higher than expected. This should normally be close to 0 volts. Since it's not, we know the fault is somewhere on the power side. I now need to check each part of the power side individually. First, I'll test the fuse. The fuse is good, as indicated by a low voltage drop. Next, I'll test the green wire. The voltage drop across the green wire is within the expected range, so it's functioning properly. Now I'll test the switch. The switch is also good, with no significant voltage drop. The voltage drop across the white wire is nearly the full source voltage, indicating that this is where the fault is located. I will now replace the white wire, and we can see that this resolves the problem. With the fault resolved, the LED now illuminates as expected. By methodically performing voltage drop tests, we've pinpointed the issue and fixed the circuit. This systematic approach ensures accuracy and builds confidence in troubleshooting skills. Now let's move to the ECU. At first glance, it may seem like a much more complicated circuit, and it is, as there's a lot going on here. But the best way to approach this type of circuit is to break it down into smaller, manageable circuits. Let's first look at how the ECU itself is powered. Like any control module, the ECU needs reliable power and ground connections to function properly. In a vehicle, it's common to find multiple power and ground ports on an ECU to ensure consistent operation and redundancy. The ECU power circuit begins at the battery, flows through the fuse, and enters the splice right node with the red banana jacks. From there, the circuit continues to the VCC port on the ECU. This path ensures that the ECU receives the voltage it needs to operate. In this configuration, the ECU serves as the load device. It consumes power to monitor inputs, process data, and control outputs. This mirrors the functionality of an electronic control unit in a vehicle, which must manage multiple inputs and outputs to operate complex systems. After powering the ECU, the circuit exits through the ground port and enters the ground block. This block serves as a distribution point for the ground connection in the system. From there, the circuit flows through the black wire into the splice left node and finally returns to the negative terminal of the battery. In vehicle ECUs, you'll often find multiple power and ground ports to ensure that the control module remains operational even if one connection becomes unstable. Ensuring proper voltage and ground at every port is a critical first step in troubleshooting any computer-controlled system. To verify that the ECU is receiving the proper voltage and has a good ground connection, we'll use a multimeter to measure the power and ground at the ECU. This is a critical step when diagnosing any control module, as the ECU relies on stable power and ground to function correctly. First, let's check the voltage at the VCC port. We'll place the multimeter's red lead on the VCC port and the black lead directly on the battery's negative terminal. In this case, we expect to see approximately 12 volts, which confirms that the ECU is receiving power from the battery. A correct reading here confirms that the power side of the ECU circuit is functioning properly, with no interruptions or significant voltage drops. Next, let's check the ground connection. we'll place the multimeter's red lead on the battery positive terminal and the black lead on the ground port of the ECU. This should also read approximately 12 volts, indicating a solid ground connection. A proper ground reading confirms that the ECU has a complete circuit back to the battery negative terminal. If the voltage at the VCC port is low, it may indicate a problem on the power side of the circuit, such as high resistance connections at the fuse or splice right node. If the ground reading is inconsistent or low, it suggests an issue on the ground side, such as a loose connection at the ground block or splice left node. When diagnosing an ECU, the power and ground readings should be fairly close to each other. Even a small difference can indicate a poor ground connection, which may prevent the ECU from functioning correctly. By performing these simple tests, we can quickly confirm whether the control module is receiving the proper voltage, allowing us to rule out basic issues before moving on to more complex diagnostics. Let's next focus on the left turn signal input circuit. This circuit starts at the battery, flows through the fuse, and reaches the splice right node with the red banana jacks. From there, the circuit flows into the splice right node with the blue banana jacks, where it then connects to the three-way switch. The circuit then continues via the white wire to input 1 on the ECU. Finally, it completes the path through the ground block and back to the battery. But what is the load in this circuit? You might initially think of the left LEDs as the load, but that's not correct. In this case, it's best to treat the input as its own circuit, separate from the output that controls the LEDs. The load for the left turn signal input circuit is actually inside the ECU. The ECU uses a resistor as the load in this input circuit. This resistor plays a crucial role in how the ECU interprets the state of the switch. When the three-way switch is rocked to the left, it closes the circuit through the white wire to input 1 on the ECU. The internal resistor drops the voltage, signaling to the ECU that the left turn signal is activated. If the switch is open, no current flows, and the resistor does not drop the voltage. This indicates to the ECU that the switch is in the off position. The right turn signal input circuit mirrors the left turn signal input circuit up to the three-way switch. From the switch, the circuit continues via the red wire to input 3 on the ECU. Like the left circuit, it completes the path through the ground block and back to the battery. The key difference is the use of the red wire in connection to input 3 on the ECU, which makes it independent of the left turn signal circuit. To demonstrate that the load in the turn signal input circuits is inside the ECU, let's measure the voltage drop at the ECU when we toggle the three-way switch to the right position. This test will help us understand how the ECU interprets the input signals and responds. To measure the voltage drop at input 3, I'll place the red lead on input 3 of the ECU and the black lead on the ground port. With the three-way switch in the off position, the multimeter displays a small voltage drop. This residual voltage reflects the ECU's internal regulation actively monitoring the input. Now let's toggle the switch to the right position. With the switch closed, the circuit completes and the multimeter shows a significant voltage drop across the ECU's internal resistor. This confirms the ECU has detected the input signal and is processing it as on. Toggling the switch back to the off position causes the voltage drop to decrease significantly, but a small residual voltage remains. This is due to the ECU's internal regulation, which continues monitoring the input signal even when the switch is off. The latching switch node provides a ground side signal to input 2 on the ECU. This type of input is common in automotive systems, where switches often complete the circuit to ground rather than directly providing power. The ground signal originates from the battery's negative terminal and flows through the splice left node. From there, it enters the latching switch. When the latching switch is closed, the circuit continues through the blue wire node and connects to input 2 on the ECU. The voltage measurement at input 2 provides an interesting insight into how the circuit operates. When the latching switch is off or open, the voltage reading at input 2 is approximately 5 volts. When the switch is closed, the voltage drops to around 0 volts. Internal to this ECU, as well as many ECUs in vehicles, is a voltage regulator. This regulator reduces the 12 volts from the power supply to 5 volts. The 5 volts is used to power the ECU's microprocessor and to provide the signal voltage for input 2. For input 2, the ECU supplies 5 volts before the internal resistor. When the latching switch is open, the 5 volts remains at input 2, indicating to the ECU that the circuit is inactive. However, when the latching switch is closed, the connection to ground causes the internal resistor to drop the 5 volts, resulting in a 0 volt signal. This signals the ECU that the ground side switch is active. Let's take a closer look at what's happening inside the ECU when the latching switch is toggled. Here I've created an illustration to help visualize the 5 volt signal and how the ECU interprets the input. In this part of the circuit, we have a 5 volt signal generated by the ECU's internal voltage regulator. This 5 volts passes through a resistor before reaching input 2. After the resistor, the ECU monitors the voltage through a line labeled voltage sense. This line measures the voltage at input 2 to determine the state of the circuit. The ECU interprets the signal and updates the switch state accordingly. In this case, the computer reads the signal as on. In this zoomed-in view, the connection to ground through the latching switch isn't immediately visible. To illustrate this, I've drawn a representation of the latching switch, branching off from the blue wire and connecting to ground. The schematic symbol for a closed switch represents the latching switch in its active state, completing the circuit. When the latching switch is closed, the circuit connects to ground. This causes the voltage across the resistor to drop, resulting in a near 0 volt signal at input 2. The ECU detects the voltage drop and interprets the signal as the latching switch being in the on position. This simple change in voltage tells the ECU exactly what's happening in the circuit, allowing it to respond accordingly. A similar process occurs on the left and right signal input circuits, but with a key difference. Instead of 5 volt source at the end of the resistor, these circuits are grounded. This zoomed-in view emphasizes the critical role of the resistor and the ECU's ability to detect and interpret voltage changes. Understanding this process is essential for diagnosing and troubleshooting input circuits in modern automotive systems effectively. Let's shift our focus to the output side of the ECU, specifically output 1. This output is responsible for powering components on the left side of the circuit, which includes 2 LEDs, the light blue small LED 1, and the dark blue large LED 1. In this circuit, the LEDs are the load, converting electrical energy into light when activated. Inside the ECU, an electronic switch connects VCC which is powered by the positive terminal of the battery, to output 1. When activated by the ECU, this switch allows power to flow through the green wire to the green splice. The splice branches the circuit to supply both LED 1 nodes. The ECU uses input signals from the switches to control this internal connection, ensuring accurate operations of the left indicator circuit. In this demonstration circuit, the activation is triggered when a connection to VCC is turned on and the ECU receives an input signal. This signal might come from a latching switch, a three-way switch, or in a real-world application, a possible external device like a key fob that flashes the lights when the car is locked. It's important to note that the key fob example represents a potential input in actual automotive systems, not the specific MMTS setup. Once the ECU processes this input, it sends power through the output 1 to the LEDs, completing the circuit and illuminating the lights. The light blue small LED 1 and dark blue LED 1 are powered via the green splice. Each LED is then grounded through the ground block, completing the circuit. As the load in this circuit, the LED drops the voltage and converts the electrical energy into light. The ground path ensures proper current flow and circuit completion. Now let's look at the right side of the circuit, controlled by output 2 of the ECU. This output powers the right side LEDs in the circuit, similar to the left side, but with a few key differences. Output 2 sends power through a yellow wire to the yellow splice. This splice branches the power to the light blue small LED 2 and the dark blue large LED 2, both located on the right side of the circuit. These LEDs are the load converting electrical energy into light, just as we saw with the left side circuit. Each LED connects to the yellow splice for power and is grounded through the ground block. This ensures proper current flow, completing the circuit and allowing the LEDs to function. The ECU turn signal circuit is made up of 6 interconnected circuits that work together to process inputs and control outputs for turn signaling and hazard indications. Each circuit plays a specific role, ensuring seamless operation and reliability. The ECU power and ground circuit. This circuit supplies the voltage and ground required to power the ECU and its internal components. The left turn input circuit. This circuit detects when the three-way switch is toggled to the left, sending a signal to input 1 on the ECU. The right turn input circuit. This circuit detects when the three-way switch is toggled to the right, sending a signal to input 3 on the ECU. The flasher input circuit. This circuit detects when the latching switch is turned on, sending a signal to input 2 on the ECU. The left turn output circuit. This circuit is controlled by output 1 on the ECU. This circuit powers the left side LEDs, signaling a left turn when the corresponding input is active. The right turn output circuit. Controlled by output 2 of the ECU, this circuit powers the right side LEDs, signaling a right turn when the corresponding input is active. Now that we've thoroughly reviewed the 6 individual circuits, we can approach diagnostics in the same systematic way we applied to the simple circuits. Let's start by introducing a fault. I've created a fault in this circuit, but I won't reveal its location. Our goal is to diagnose and fix the issue using the same systematic techniques you would apply in real-world scenarios. Let's start by verifying the problem and analyzing the circuits to develop our diagnostic plan. In this scenario, the left LEDs aren't functioning properly. The right LEDs operate as expected, but the left LEDs remain off when the three-way switch is toggled to the left position. We start by verifying the problem. Toggling the three-way switch to the right successfully activates the right LEDs, but toggling to the left fails to illuminate the left LEDs. Next, let's test the latching switch to see if it activates the left LEDs. When I toggle the latching switch to the on position, the left LEDs illuminate as expected. This confirms that the ECU's output to the left LEDs is functioning properly and that the problem lies specifically with the left turn input circuit. In our simple circuit, we always started at the load for our testing. In this case, the load for the left turn input circuit is the internal resistor. Let's perform a voltage drop test on the load in the circuit. We'll measure the voltage drop across the ECU, specifically from input 1 to ground. For a properly functioning circuit, the voltage drop across the ECU's internal resistor, the load, should be close to source voltage. In this case, the voltage drop across the ECU is close to 0 volts. This result tells us that the internal resistor in the ECU is not acting as the load. Instead, the issue lies elsewhere in the circuit, on the power side or the ground side of the circuit. Let's now check the ground side of the circuit. Place the red probe on the ground terminal of the ECU and the black probe on the battery's negative terminal. A properly functioning ground side will show a low voltage drop, indicating minimal resistance. The voltage drop on the ground side is close to 0 volts, confirming that the ground circuit is intact. This allows us to shift our focus to the power side of the circuit. Finally, we'll test the power side of the left turn input circuit. Place the black probe on input 1 of the ECU and the red probe on battery positive. For a properly functioning circuit, the voltage drop should be low, indicating minimal resistance along the power side. Here the voltage drop is around the full source voltage. This indicates that there is an issue on the power side of the left turn input circuit. Given the results, we'll inspect the power side of the circuit. The issue is likely in the white wire connecting the three-way switch to input 1 of the ECU or the three-way switch's left position. The reason we should suspect these is that all other components are shared with the right side input circuit. Let's start with a voltage drop test on the white wire. When we perform a voltage drop test on the white wire, the multimeter reads close to the full source voltage. This confirms that the white wire has a problem. In a properly functioning circuit, the voltage drop across a wire should be close to 0 volts, indicating minimal resistance. After repairing the fault in the white wire, we retested the circuit. Toggling the three-way switch to the left now successfully illuminates the left LEDs. This diagnostic process highlights the importance of systematic voltage drop testing in identifying faults in automotive electrical systems. By isolating the issue to the power side, we effectively resolve the problem and restore the circuit's functionality. We'll now apply the same systematic approach to diagnose a new fault in the right turn signal output circuit. A fault has been introduced into the system, and its location is unknown. Our goal is to identify and resolve the issue through structured testing. Let's begin by verifying the problem and analyzing the circuit. We start by verifying the issue. When toggling the three-way switch to the left LEDs illuminate as expected. However, toggling it to the right does not activate the right LEDs. Similarly, Activating the latching switch successfully turns on the left LEDs, but no effect on the right LEDs. This points us towards a potential issue in the right turn signal output circuit. Let's begin by performing a voltage drop test across the load, which in this circuit is the right LEDs. Place the red probe on the power side of the LEDs and the black probe on the ground side of the LEDs. In a properly functioning circuit, the voltage drop across the LEDs should be close to source voltage when the right output circuit is active. The voltage drop across the LEDs is close to 0 volts. This indicates that the LEDs are not receiving sufficient voltage to operate. This suggests the fault is either on the power side, preventing voltage delivery, or on the ground side, disrupting the circuit's completion. Next, let's test the ground side of the circuit. Place the red probe on the ground side of the right LEDs and the black probe on the battery negative terminal. In a properly functioning circuit, the voltage drop on the ground side should be close to 0 volts, indicating minimal resistance. The voltage drop on the ground side is close to 0 volts, confirming that the ground circuit is functioning properly. With the ground side verified, we'll now shift our focus to the power side of the circuit to locate the fault. Let's now check the power side of the circuit. Place the black probe on the power side of the right LEDs and the red probe on the battery's positive terminal. In a properly functioning circuit, the voltage drop on the power side should be close to 0 volts, indicating minimal resistance along the path. The voltage drop on the power side is close to the source voltage. This indicates there is excessive resistance or an open on the power side of the circuit. To pinpoint the fault, we'll now test individual components along the power side. The first component on the power side of the circuit that is not shared with other circuits is the ECU, specifically the out-to part of the ECU. Inside the ECU, an electronic switch connects the battery positive, VCC, to out-to. This switch turns on and off to blink the LEDs. Let's test the voltage drop across this internal switch. Place the red meter lead on the VCC terminal and the black meter lead on out-to. The voltage drop across the internal switch in the ECU is higher than expected. A properly functioning switch should have very little resistance and therefore a minimal voltage drop. This excessive voltage drop indicates that the internal switch in the ECU is faulty. Unfortunately, this would require the replacement of the ECU to resolve the issue. To better understand the behavior of a properly functioning electronic switch, let's measure the voltage drop across out-1, which is operating correctly. Place the red lead on the VCC terminal and the black lead on out-1. Notice how the voltage drop alternates between full source voltage and 0 volts as the LEDs blink. When the switch is in the open position, we see the full source voltage of 12 volts. When the switch is in the closed position, the voltage drop is 0 volts, indicating very little resistance. This behavior confirms that the switch in output 1 is functioning as expected. In contrast, the voltage drop at out-2 does not follow this expected pattern. Instead of alternating between 12 volts and 0 volts, this behavior indicates a fault in the internal switch. This confirms that the switch at out-2 is faulty and requires replacement of the ECU. This diagnostic process demonstrates the value of a systematic approach when troubleshooting computer-controlled electrical systems. With the MMTS, we replicated real-world scenarios and used structured tests like voltage drop measurements to isolate and identify faults effectively. The methods we applied here mirror the steps you should take when diagnosing faults in real-world ECU-controlled systems. Always break down the circuit into smaller, manageable components, start with the load, and systematically test the power and ground paths. These principles ensure accuracy and efficiency, whether you're working with training systems or diagnosing vehicles in the field. The MMTS offers a hands-on way to bridge the gap between theory and practice, building the confidence and skills needed to diagnose even the most complex automotive electrical systems. By mastering these diagnostic techniques here, you'll be better prepared to troubleshoot and repair real-world vehicles. Thank you for exploring the MMTS with me. Diagnosing computer-controlled systems requires a structured approach and the right tools to succeed. By practicing these methods consistently, you'll gain the confidence and skills needed to address even the most complex diagnostic challenges effectively.
At Weber State University, your expertise counts. Save up to $14,000 in tuition and fees by getting college credit for a completed ASE certifications such as Automotive and Light Truck Certification, A-Series, Light Duty Hybrid Electric, L3, Medium Heavy Truck, T-Series, Military Tactical Wheeled Vehicle, MIL2 through MIL8, XEV Safety Certification, Level 1 and 2. We also accept Air University and Joint Service Transcript credits. For more information, please visit weber.edu/ASE.